So now it's time for Powell Walker. Sorry. So Powell is a release engineer at Samsung on the Tizen platform, which is a mobile phone. And Pavel will talk about testing remote embedded device. Mike is yours.
Thank you. Hello, everyone. As I was introduced, I work at Samsung R&D Institute Poland, and I'm currently involved in Tizen release engineering team. That's why we have to automate as much as possible in order to stay efficient with our day-to-day activities. That's also why we came up with the design for unification for testing automation on embedded devices, which we call MuxPi, and that's what I would like to share with you today. Let me start with a short introduction to what I will be actually talking about. Then I will summarize previous efforts in this matter. I will depict our idea for testing automation on embedded devices. Then I'll go through the hardware that we made, software, accompanying software as well, and I would like to share with you our future plans for the work that we still have to do. I will summarize it with a short conclusion, and then we'll have a Q&A session. So, what do I actually do? I work with Tizen, which is a GNU Linux distribution for embedded devices. It is based on standard components like GNU Tools collection, Linux kernel, obviously, Wayland server, Wayland display server, and Enlightenment Foundation libraries, or EFL in short, as the main graphics library. And Tizen is mainly used on consumer devices like mobile phones, wearables as well, but also TVs, fridges, as in Family Hub, and since May 2017 with Tizen 4.0 Milestone 1 on IoT devices as well. But Tizen on those devices is a product one grade Tizen. What I do is work on platform, which is being developed by contributors all over the world with R&D centers in India, USA, South Korea, and Poland as well. That's why we need to develop our platform continuously with daily snapshots of merged software. But the fact that we release often in order to fail early does not mean that we take the QA stage lightly. Because we have to take care of devices for developers all over the world, we always check the software that we are to publish on actual devices before the images are published for everyone to use. And even though packages are equipped with internal tests and we run them on a daily basis, they are not enough. And because we want no unexpected behavior of developers' devices, that's why we make sure that there is no. And how does it look like? We monitor pre-releases of the software, download them, flash onto the target devices, then run test batteries, gather results, and investigate if there were any failures or other indicators that the software should be stopped from being published. But in order to do that, it is much easier not to just have all of those devices, various devices, mobiles, wearables, or even fridges right on the desk of release engineers. It is much easier to have them being accessible remotely. It is especially important for the devices that are not published yet, that they really need to be stored in a secure manner. But it also gives us the ability to have much less effort on the developer side as for the maintenance of the devices, and all of them can be much better utilized when they are shared, when they are never pointlessly stored in some developer's locker once he or she goes back home. That's why we came up with this device. It's MuxPi, and it needs only two interfaces, two connections, in order to be accessible remotely, which are power supply, of course, and the Ethernet for network connection. Once connected to the target device, such as Raspberry Pi 3, right here, it is already ready to use, and it's, as you might suspect, pretty easy to scale, because it needs only two interfaces. So scaling up is as easy as connecting further MuxPis with target devices to the network switch, and it unifies the access to the boards. So it's easy for Raspberry Pis or other single board computers such as Odroid, or even other types of target devices like mobile phones. And we will get back to the MuxPis in a minute, but before, let me summarize real quick why did we came up with this design, and what else can be used for automated testing. From software point of view, one of the most popular applications for that use is LAVA, which stands for Linaro Automated Validation Architecture, and is being developed by the company Linaro. It is an automation system for operating system deployments, and supports both virtual and physical devices, and allows running bootloader, and system level tests as well, although some additional hardware might be necessary for them to work properly. However, what was a problem for us was being able to run interactive sessions on boards that were connected to the Lava server. Lava has an internal mechanism for interactive sessions, which is called hacking sessions, but it did not work for our use cases, which involved modification of bootloader or rerunning or restarting device over and over again. For us, it was to test recovery mechanism of Tizen platform. However, it is widely used at Linaro, of course, for automotive-grade Linux test lab system, and for other popular GNU Linux distributions, such as Debian or Yocto as well. I believe the most popular use case is kernel CI, with already 3.5 million successful boots and counting. And that's not the only effort from Linaro to automate testing on embedded devices. In 2013, they also came up with LMPs, which are boards for both testing hot plugging devices and checking how the software on embedded device react to hot plugging, for example, SATA device or USB device, but also they were able to give much better control to the administrator of testing laboratory over the device under test, or DAT for short. But it is currently on hold, and lessons learned from use of LMPs, especially of microSD card demultiplexer, were published in the link down below. However, we also gave an attempt at creating microSD card demultiplexer, or SDMax for short, and we've been using it since 2016. This board only gives you the ability to share access to the microSD card between device under tests, or DAT for short, and test server, or TS. It also allows to control the power supply to the target device, and that's basically it. It does not know anything else about target device, and it only gives you this to small features. However, it was pretty useful for us, and not only for us. Qt company and also Ableton, which you might have heard of, were able to recreate this setup because we thought it would be great to share it with others, and we published all the schematics and software and other related materials in the Git repository, and used only open source software for that so that everyone can use it, or even fork it, like Resin.io, who thought that it would be great to have some indicators on board and created AutoHAT board on the basis of our SDMux. Unfortunately, we ran into some issues using SDMuxes, and the main issue that we got was the instability of the connection on the USB between the SDMux and test server. Every 3 to 6 months, the test server was unable to enumerate another devices on the USB hubs, and that the 71 errors are protocol errors, which you can see, which led to downtimes of our testing laboratory, which we were not all right with. That's why we took a step back, went back to drawing board, and decided to bring a new idea to the table. We already knew what was working right. We also knew what wasn't. And that's why we decided that we will keep only replaceable medias, which were off the quickest in testing laboratory. So we still are using micro SD cards for the deployments of operating system images, but we decided that there shouldn't be a situation where a failure of a single device causes a failure of the next ones. So we try not to introduce any SPOF onto the setup. And we also knew that there has to be no involvement of the USB connections on the test server side. We also wanted minimum external connections between the device under target or the board that controls it and outside world, and wanted to have it in a unified way. With the feedback we got from Resin.io, we decided that easy setup and maintenance would be a great plus. And since we were back at the drawing board, we thought that maybe a whole user interface would be helpful. And with increasing demand for measuring and lowering, of course, power consumption, we decided that it could be useful as well as having and being able to write some EDID information to HDMI. It's pretty useful for the devices that you would like to, for them to think that they have display connected even though they don't. That's why we came up with this design, but I think it would be easier to describe it on the schematics. We started with the good old SDMux, which has already simple UI added to the board itself, and of course the power control and power consumption measurement on board as well. Everything is under control by the NanoPi Neo board, which is a simple single board computer, ARM7 based, ARMv7, and of course a microcontroller for low-level features of the board itself. With the MuxPi board, we are able to demultiplex the connection of microSD card between DAT and TS. We are also able to switch power supply, and that's what SDMux already gave us. We are also able to switch dynamically jumpers on the DAT, which is pretty useful if your device has some buttons which are required to be pressed in order for that to boot up or to be put into the download state for flashing device or so. We also have got hardware for measuring power consumption and the ability to write fake DID to the device under test over HDMI connection. We also provide multiple ways of connecting to the device under test via USB, Ethernet, microSD card, of course, or if you need a serial console directly to your device under test, that's also available as well. And we wanted the MuxPis to be able to interact with testing laboratory maintainer. That's why it is equipped not only with activity LEDs, such as SD reader LED or power LED, which were suggested by Resin.io, but also RGB LEDs on the bottom left corner for indicating state of the device, not only MuxPi, but also a device under test, and also OLED display for simple messages. We also put a couple of buttons to be able to interact quickly with the whole setup. It gave us easy maintenance over the Dryad, which we call MuxPi board connected with target device. But we knew that not everything can be predicted before those boards go into production. That's why we decided to be able to extend them from start. And that's why we use the prototype boards for quick setups if there is a need for a new device on board or just rearrange something quickly. With all that, we've got finally an independent controller for devices under tests, which does not require any test server, which is aware of its state and can indicate any failures or unexpected behaviors, which is also easy to maintain and extensible from the ground up if there is a need to be extended. And if you'd like your own, well, you'll have to equip yourself with a NanoPi Neo for controlling it for about $10 with parts for the MuxPi board. And the $80 price was for our initial batch, which was about 30 boards, but also some high soldering skills and a lot of patience. But if you are still interested, go ahead to git Tizen.org to our repository and check the schematics out. But hardware is not everything that had to be provided in order to have the automating testing laboratories for embedded devices. We also had to implement some accompanying software. And with previous efforts I mentioned, for example, Lava, which is a monolith, we decided that it is hard to extend it in future. So a multi-tier architecture was chosen for the software to control test farm. We also wanted to follow the Unix philosophy, and each tool does only one thing, but we hope that it does it well. We wanted them to be able to communicate and to be easily swapped if there is a need to provide a new tool. So they all communicate over HTTP APIs. But still, we wanted to have a simple and similar solution stack, and everything is written in Go language. And as I mentioned earlier, how does the testing look like? That's why we provided 4 layers for testing laboratory. I mentioned that we have to monitor and download all of the software to be tested. And who knows how to do that? That's the role for Perun. Perun is a character from Slavic legends. It's a demigod who has the most power and most responsibilities of all others. And who knows which actions are necessary? That's the work of Veles. Veles in Slavic legends is the one who takes care of the underworld. As for the tasks, where can it be done? That's the work for Boruta. Boruta is a caretaker in Slavic legends and takes care of all living creatures in forests. And as for how to actually do that, that's the work on hardware level and actually MuxPi, which does not follow the Slavic legends because it was invented independently much earlier. And let's begin with MuxPi, which actually allows us to create automatic testing laboratories. It manages single device under tests and is fully aware of its capabilities, whether it has a display connected or not, which interfaces does it provide, and so on and so forth. It requires only two interfaces, as I mentioned before, which are power supply and the Ethernet for network connection. Together with device under tests, we call it a dryad, which also is from Slavic legends. As for the software to manage dryads, we provide two tools. First one to be able to put operating system images or flash over the air to the devices, and also to the other one to control power supply to the target device to put the device into known state and be able to control it. And with all those over all those dryads, we've got Boruta, which takes care of the whole farm of multiple dryads. It can schedule access requests to the devices, and it provides a convenient way of accessing selected dryads when it is given. Single Boruta server takes care of multiple dryads, and a single dryad hooked up into the Boruta server starts in maintenance mode, which is then moved to the idle or unallocated by the testing laboratory maintainer. If such dryad matches requirements for the access requests, then Boruta prepares environment for that, setups tunnel or SSH tunnel or other way of connecting to the device under test if it is necessary, and then actions can be performed on the target devices directly. Once they are finished, devices go back into the unallocated state and can be reused after that. But I believe no one wants to do that on their own all the time. That's why we also provided a Veles, which is a lightweight testing framework inspired by Lava, and it provides similar to Lava interface based on YAML job definitions, which we try to stay as close as possible to the Lava syntax. So we also allow the same stages of device under tests, which are deployment, boot, test, and of course collection of the results. Single Veles server should be connected to the Boruta, and then Boruta, who controls dryads, can execute all those tests. And with such setup, we've got it pretty similar to the one that Lava provides, because from VLS YAML job definitions goes in, then they're all executed right down to the target devices, and the gathered results are brought back by the VLS web interface. And that's actually its main purpose, to automate the actions that are being performed on the device under tests. Actually, that's all that VLS provides. It only parses a YAML job definition, collects all the assets that are necessary for the job to be completed, requests access to the device under tests from Boruta, and then perform the actual actions. But I also mentioned that there should be a layer which actually has to know what should be done. And that's the work for Perun, which is our layer for, or maybe a dashboard would be a better word, for actually testing the operating system images, which schedules the verification on the basis of what is being pre-published for Tizen. Perun is the layer that actually automates the quality assurance step of what we do at Tizen every day, so the release engineering duties. Perun also has to be connected directly to the VLS server, and that's how Perun provides us with results. It crawls a single URL with operating system images, reports any change that could be detected, submits VLS jobs on those detected changes, collects artifacts from the test execution, interprets them so that we won't have to, and that's how we know whether a new release can be published or not. And with this layered setup, we think that it's kept pretty simple, but also decoupled. If you only need software to, and hardware of course, to unify access to your various target devices, then go ahead, just take MuxPis, connect them to your devices, and with two interfaces, power supply and network connection, you'll have access to them remotely. If you already have such hardware and you don't want our, then replace it with your own, but maybe you would like to be able to schedule your tasks or schedule remote access requests. And for that, you might find our Boruta useful. Or maybe you already have your own testing framework and you do not want VLS, but Boruta with MuxPis would be pretty useful. Or maybe you think that our Golang implementation should be reworked, and you have already your JavaScript dashboard, your Python-based testing framework, and you schedule access to the devices under tests with Java Jenkins. But maybe the MuxPi would be the hardware you would like to use for the unification of your environment. That is also possible as long as the communication over HTTP APIs is set with the specification we provided. So that's what we've been working so far. And what about the future? We will focus on the audio I/O and testing the audio functions of the single board computers and other embedded devices as well. We will investigate the possibility of having USB Type-C as more and more devices are equipped with it, and it could be pretty useful. And for the better control over the dryads, we also think about having a serial console with embedded converter on the board itself. As for the software side, we will provide convenient web interfaces for current layers, since what we currently have are only CLI tools. We also want to provide service state management in case there are some failures on the server side, and also provide a new layer or even more of them to automate the whole setup further. And if you'd like to know more about those devices, go ahead to our wiki pages, or you might also, where you might also find our lessons learned from the SDMux board. If you have some questions, go ahead and drop us a line at mailing list or poke us at IRC channel Tizen on Freenode. So to sum it all up, we currently got a setup which can be quickly made and is pretty easy to maintain. We finally divided all the responsibilities that are in testing laboratory, and no developer has to do it, has to do them all by himself. We've got parallel execution of all those tests on target devices and sharing devices for better utilization, and a unified environment which we've been pretty happy with so far. If you have any questions about this board or software or the laboratory setup, I would be now more than happy to answer them.
How many physical devices do you have in this system at the moment?
All right. The question is how many devices do we have in our testing laboratory? And currently, I believe it's around 50. The next batch would add around 100, but we never went with more so far.
Did you try to run Lava Dispatcher on those boards if you had the usual user that would be possible?
The question is about Lava Dispatcher and running it on the MuxPi board. We haven't tried it, but it would be possible. If you ran Debian on the NanoPi board and got Lava Dispatcher packages directly from Lava maintainers, because it's already prepackaged in the repository, if I'm not mistaken. So yeah, that would be possible. We just haven't tried it yet. We focused on the Boruta Veles Perun stack.
How much current does it provide to the device on your test? How much? Is there any maximum that you can provide from MuxPi?
As far as I know, there is. Oh, yeah, sorry. The question was about the maximum power that can be provided to the target device. And as far as I know, there is no limit. But I believe that it would be much safer to ask that on the mailing list directly to the board designer. Yeah?
I mentioned that a few people in this group that I think necessary a few weeks ago and make one of these boards. And obviously it would be more efficient to make one batch. So I was just wondering whether it would be okay to like post on your mailing list so people can put something like this to coordinate
All right, so the question was about making a bigger batch of MuxPi boards and about gathering all interested on the Tizen mailing list. Tizen is an open source project, so everyone is invited to discuss and to post new information there. So I see nothing that could prevent from it.
How about reading the HDMI image from the HDMI port? They transfer that?
All right, the question was about the HDMI on the board and getting image from the HDMI. Currently, only the PCC line is connected for the EDID information, and it's having the image over the HDMI is a complex topic, and for now it's out of our current scope. Sorry.
Okay, no more questions? Okay, thank you, Paweł.
Thank you for